Did you know a 10 microfarad ceramic capacitor may actually only give you 1 microfarad, even if you follow all datasheet rules? Two hidden effects can slash your capacitance by up to 90%, and I was shocked when I learned this well into my 31-year professional career. Imagine how much a 90% capacitance reduction can do to your project. So in this video I'm going to show you exactly what these two killers are and how you can measure them yourself or quickly look up the data online. So you don't end up with only 10% of the capacitance you expected and a project heading for disaster. So let's have a look at measurement results on the first effect, which is caused by temperature. In this graph you see the measurement results of the temperature response of several different capacitors. The scale is relative to the capacitance value at 25 degrees. So the capacitance at 25 degrees shows as 100%. So you can see huge differences between different types of dielectrics. For the COG capacitor, my equipment literally was not able to detect any difference over temperature. The Y5V capacitor, however, loses almost 60% of its value, and it's rated for 85 degrees, so we're not doing anything wrong with it, we're well within normal operating conditions. Another interesting effect you see here is that after a heating cycle, the values of some capacitors have dropped. When you heat a class 2 type ceramic capacitor, I'll explain that in a minute, the internal structure changes, leading to a capacitance value change. You also see that the initial value can be quite far off, plus 35% for the Y5V capacitor. Ceramic capacitors come in two main classes, class 1 and class 2. They really got adventurous here coming up with these. Ceramic capacitor types are indicated by 3 character designations. Class 1 ceramic capacitors are fantastic. They're incredibly stable under all conditions. You can recognize them because one of the 3 characters is a 0, which indicates a 0 temperature coefficient. The drawback of these is that you can only get them in small values. Class 2 capacitors, on the other hand, can be absolutely horrible when it comes to stability if you pick the wrong one. The advantage of these is that you can get them in very high values, which you almost always need in your designs. So how do you know what you're going to get? Class 1 is not an issue, they're rock solid. For Class 2, the designator can tell you exactly what temperature degradation you can expect. You can see it in this table. So each character tells you something. The first character tells you the minimum temperature, the second character tells you the maximum temperature, and the third character tells you the capacitance tolerance that is allowed to occur within that temperature range. You can see how it works in the example in the left bottom. Now it's nice to check if these designations actually fit with the measurements. In this graph you see the expectant tolerance based on the designations, and it nicely fits with the measurements. The COG is best, the temperature coefficient is not 0, but my equipment can't measure it. The Y5V is worst, but it only loses 58%. It could have been much worse. The X7R is better than the X5R because of the higher maximum temperature. So how do you solve temperature derating issues? By the way, derating is the technical term for capacitance reduction due to operating conditions. Well, just pick a more stable class 2 capacitor. You know how to do that now. You could also use a capacitor with a much larger temperature range than you actually need. Or you could pick a much bigger value than you need. So even though the value gets reduced, you still get the capacitance you need. You could also use a class 1 capacitor if the value is small enough and you're willing to pay for it. They are more expensive, but sometimes you absolutely need the stability of a class 1 capacitor because your circuit simply won't work without it. Now measuring this kind of reduction due to temperature is already bad, but the next effect I'm going to talk about has an even more devastating effect. I actually measured an 89% drop in capacitance while staying within datasheet operating conditions. Before I show you that 89% drop, I've got 2 free gifts for you. My electronic product development checklist developed for over 30 years and a $500 free module from my professional course. Both are in the link below. Just grab them with your email and I'll send you more design tips and offers in the near future. Alright, so what's behind this 89% drop? It's called DC bias derating. This is the reduction in capacitance caused by applying a DC voltage across a capacitor. And here's the problem. Capacitors are pretty useless if you don't have a bias voltage across them. Let me show you the measurement results I got with the same 4 capacitors. Pay attention to the pink line, nearly 90% reduction at 6 volts for a 6.3 volt capacitor. At 3 volts, this thing has already lost 75% of its capacitance. Imagine having this capacitor at your 3.3 volt DC-DC converter output. You expect to get 10 microfarad, but you get 2.5 instead, basically quadrupling the ripple on your supply, ruining circuit performance and possibly creating a huge EMC problem. This can be a disaster, especially if you don't understand why this happens. So it would be nice if you had an idea of what factors impact derating. Basically, the more capacitance times rated voltage you try to cram into a certain volume, the bigger the problem gets. It's illustrated with this formula. This formula is just an indication to give you a direction. You can't easily say there is a certain value above which you get a certain derating if you were to plug in actual values. There are huge tolerances on this between different capacitor types and manufacturers. There's also a limit to how much capacitance you can cram into a certain volume given a certain operating voltage. You can see practical values in these tables. In the upper table you see the maximum capacitance you can find versus package size at a rated voltage of 6.3 volts. The DC bias derating is shown at 3.3 and 6.3 volts. Also interesting to see how much bang do you get for your buck. The 0603 in this case is 2 times more economical than any other package. So if you do large volume production where price is a thing, it's good to check this as well. Now often you don't have a choice in package size. A fine pitch component like an FPGA or CPU may force you to use a 0201 package, you can't fit it otherwise, limiting your options. In the bottom table we see the effects of reducing capacitance while keeping the package size and rated voltage the same. Derating does improve if you reduce the capacitance. Note that at some point Murata switches to another dielectric type. There's also a clear economical winner here. 22 microfarad is twice as cheap per microfarad as the other values. Maybe this value is produced in ridiculous amounts at the moment, making it cheap. So if you want to find these specs yourself, you can use SimSurfing from Murata. I'll leave the link in the description. You simply fill in the component order code or use the filter options to find the capacitor you want. Then press CDC bias and then cap change to get the graph that shows you how capacitance changes with bias voltage. So now you know how you can get bias derating information from the internet. Measuring these derating numbers myself was a little challenging, and I'll show you in a moment what setups I tried and what I used in the end. I also tried bias and temperature derating at the same time with very unexpected results. But first let's have a look at a practical approach for selecting decoupling capacitors. I'm talking about decoupling here because that's the most common use case for large value ceramic capacitors. So in order to do that you need to take a few steps. First you find out what capacitance and voltage you need. Next, you figure out what size restrictions you have on your components. Then you find the maximum values for those sizes and check the DC and temperature derating values. Now, if you can achieve the needed value with a single capacitor, then you're done. Otherwise, you have to use multiple capacitors in parallel. Sometimes you're forced to use a very small package, near a fine pitch IC for instance. So you find the biggest value in that package and place that as close as possible to the IC. Then you place higher value capacitors in bigger packages further away, preferably as close as possible, to create the total capacitance you need. Finally, you can check if there are any big price optimizations you can do. For high volume production, that can make a big difference. So now that you know how to do that, let's see what happens if you combine DC and temperature derating at the same time. So for the worst capacitor I tested, the 10 microfarad Y5V, I tried applying maximum DC bias and temperature at the same time, and something very interesting happened. With just the DC bias alone, you saw a derating of 89%. However, when I applied 85 degrees, the derating reduced to 84%. I expected the derating to get worse, but heating it up actually compensated the loss of capacitance a little bit. This shows you how all over the place these capacitors are in reality. Now let's look at the measurement setup and the challenges I had with it. So I started out with this schematic and PCB. The idea here is that you can apply DC bias using the lab supply via two 150 kilo ohm resistors. The values are so large that this will not affect the capacitance measurement, while the leakage of these capacitors is so low that no voltage drop will occur over these 150 kilo ohm resistors. You can then measure the capacitance using an RLC meter via a 220 microfarad aluminium polymer capacitor. Putting this capacitor in series with the capacitor under test, the DUT, will reduce the overall capacitance you measure. This works fine if the 220 microfarad capacitor has a stable value, so you can calibrate for it. The interesting thing is that when you heat this whole board up, you find out that this capacitor has a pretty large positive temperature coefficient of around 10 to 20%. This kind of ruins the measurement accuracy, so you have to look for something else. So how do you solve that? With three changes. First, you use a really big capacitor, 2200 microfarad in this case. This means it's so big that even if the value changes, it's hardly going to affect the combined value of this capacitor in series with the DUT. Second, place this capacitor further away so it hardly heats up at all. We're only heating the area around the DUT. Now this large capacitor allows for a very nice third change. Use the capacitor to provide the DC bias. When you charge it up using a lab supply to 6 volt for instance, The large value and low leakage means that the voltage will remain stable for a very long time. I checked this and it works perfectly. Another advantage is that when you're measuring, the lab supply is completely disconnected, removing any chance of it influencing the measurement. I also kept two resistors of 470K to check the DC bias voltage with a multimeter. The multimeter is normally not connected. When measuring, however, you have to be careful. A multimeter often has an input resistance of 10 mega ohm. So with the two 470K resistors, that creates a voltage divider, causing you to measure a lower bias voltage. You have to compensate for that. In the picture for the actual setup, you also see a thermocouple placed very closely to the DOT in order to measure the temperature. In this picture you can see the total setup. The lab supply to charge the capacitor, a multimeter to read the temperature from the thermocouple, an RLC meter to measure the capacitance, and a tripod to hold a hot air solder gun right above the board to heat the device under test. The rest of the SMD hot air station is not shown in this picture. Setting the temperature is a bit annoying in this setup, as you have to wait quite a long time before the temperature stabilizes. It's primitive, but it works fine. So you've seen that capacitor values may not be what is advertised and that this can really ruin your circuit. And it can keep you scratching your head for quite some time if you're not aware of it. In the next video, I'll show you why the most common decoupling strategy doesn't work and what you can do instead. You can see that right here. And if you want to take your electronic skills to the next level, check out my course. Link is in the description. See you next time.